What you're looking at on the screen is a model of a wellbore trajectory. Notice how it bends and snakes as it works its way towards the total depth. Each one of these bends is a dogleg, and the severity of the dogleg is a function of how fast the well bends over a measured depth interval. Now, since it's underground, we can't physically see how fast the wellbore is turning. Instead, we depend on our MWD measurements, specifically inclination and azimuth, to determine the curvature of the well. There are many ways this curvature can be calculated, but the method we're going to use today will be the minimum curvature method, which over the past several years has been the standard way of determining the wellbore trajectory as well as the dogleg severity. Now, minimum curvature works one survey interval at a time, and each interval has two survey stations. Station 1 gives us the wellbore direction at the beginning of the interval, and Station 2 gives us the direction at the end of the interval. The measured depth difference tells us the length of that interval along the wellbore. The key idea is that each station's inclination and azimuth can be converted into a direction vector. So instead of just comparing angles, minimum curvature compares two direction arrows, one at Station 1 and one at Station 2. Now we have each survey station written as a direction vector. But how are the components in each of these vector matrices determined? To answer that, let's take a step back and look at how inclination and azimuth break the wellbore direction into its north, east, and vertical parts. Let's start with inclination. In oil and gas, inclination is measured from vertical. So if the well is going straight down, the inclination is 0 degrees. As the well turns away from vertical, the inclination increases. That means inclination can tell us how much of the wellbore direction is vertical and how much of it is horizontal. The vertical component comes from the cosine of inclination. The horizontal component comes from the sine of inclination. So inclination gives us the split between vertical movement and horizontal movement. But horizontal movement itself still has two parts, north and east, and that's where azimuth comes in. Azimuth tells us the direction the horizontal piece is pointing. So we take the horizontal component, which was the sine of inclination, and split it into north and east using azimuth. The north component becomes the sine of inclination times the cosine of azimuth. The east component becomes the sine of inclination times the sine of azimuth, and the vertical component stays cosine of inclination. Now we're back at the spot where we have those two arrows. And remember, the first one represents the wellbore direction at Station 1, and the other one represents the wellbore direction at Station 2. Now the question is, how much did the wellbore direction change between those two stations? To see that, we line up the tails of the two vectors. The angle between them is the dogleg angle. Now remember, these two arrows represent the wellbore direction at two different survey stations. And as the arrows move, the angle between them changes. If the arrows are almost aligned, the wellbore direction barely changed, so the dogleg is small. If the arrows spread further apart, the direction changed more, and the dogleg is larger. So the first thing minimum curvature needs is the angle between the two direction vectors. That angle is what we calculate using the dot product. The dot product is really just a way to compare two vectors. We take the north part of the first vector times the north part of the second vector. We do the same thing for east, and the same thing for vertical. And after that, we add those three pieces together. That one number tells us how closely those two vectors are pointing in the same direction. Since both vectors have the same length of 1, the dot product equals the cosine of the angle between them. So the dogleg angle is found by taking the inverse cosine of that dot product. As the terms move around, we're just reorganizing the equation, combining like terms and using basic trig identities to simplify the expression. The end result is a dogleg angle, which is what we were looking for this entire time. At this point, beta, which is the dogleg angle, only tells us how much the wellbore direction has changed between the two survey stations. But dogleg severity also depends on distance. The same angle change could be gentle with a low dogleg severity over a long interval, or sharp with a high dogleg severity over a short interval. So we divide the dogleg angle by the measured depth interval, then scale it to a standard length. In field units, that standard is usually 100 feet. So dogleg severity is beta divided by the change in measured depth times 100. So there you have it. Most of us have seen the dogleg severity equation before, but this is how it's actually derived. We start with the inclination and azimuth at two survey stations, turn them into direction vectors, use a dot product to find the angle between them, and then convert that angle into dogleg severity. Beta tells us how much the wellbore direction has changed. Dogleg severity tells us how quickly that change happened.